We are still in Unit 9. Yesterday, or in our last lesson, we did Section 1, Review of Known Integration Techniques. Today, we do integration by parts. This is a really nice, interesting section. So, I did give you a notes page, and if you grab that, we can kind of, I'm going to introduce it to you on this notes page. So, integration by parts. Integration by parts, this is notes 2. So integration by parts. This technique was developed by Brooke Taylor. He is also responsible for Taylor series and polynomials, which you will learn quite a bit about. That's our Unit 12. So in just a few units, we'll be doing Taylor series and polynomials, which are fascinating. Anyway, the name Taylor will be very familiar to you. Anyway, Taylor also developed integration by parts. Okay, this technique is very useful when it can be used for many functions, but we use it the most when we have our integrand is an algebraic times a transcendental function. So like 3x to the fourth times sine of 3x, tangent 3x, cosine 3x, things like that. Another transcendental function is e to the x. So like if you had algebraic times an e to the x, that would be a good kind of cue to try integration by parts. Okay. Another transcendental function is natural log, or all of the logs. So transcendentals are the trig functions, the inverse trig functions, the exponentials, and the logarithmics. Okay? So that's your cue to use integration by parts. Or when you have a product of two transcendental functions, two different transcendental functions. Maybe e to the x times a sine, or a sine times a natural log, or an e times a natural log. So those are cues also to use integration by parts. But the theory behind integration by parts, it works for everything, okay? The theory is the theory, so it's not just for those situations. All right, let me show you where this comes from, okay? Let's find the derivative with respect to x of u times v, where u and v are both functions of x. So u and v are functions of x. Okay? So we would use the product rule. So we would start with u and take the derivative of u with respect to x. And then you'd multiply that by the v, right? And then you would leave u alone and multiply by the derivative of v, right? So that's just applying the product rule. Okay, now what I'm going to do, I'm going to move this v du dx, I'm going to move that to the other side. So I'm going to have the derivative with respect to x of uv minus v times the derivative of u with respect to x is equal to u dv dx, right? And now I'm just going to switch sides. I want this term to be over here. Okay, just switch sides. Now I'm going to integrate both sides with respect to x. All right. When I integrate this side with respect to x, do you see how the dx's cancel? And we're left with the integral of u dv. Okay. On this side, what do we have? Well, for this piece, the dx's go away, right? We just have the derivative the derivative of uv, and we're taking the antiderivative of the derivative of uv, and those cancel each other out, don't they? That's just uv plus c, which we always get when we have an antiderivative, right? Okay? So that's just uv, because it's the integral of the derivative of uv. Okay? Over on this piece, the dx's cancel, and we have minus, we can't take the antiderivative, so it's still the integral of v du. This is our formula for integration by parts. And I need you to know it. Okay? The integral of u dv is uv, and if we were in class, we would repeat this about 5 times, and I would have you guys repeat it. uv minus integral v du. You've got to know that. So right now, pause the video and repeat that 5 times. uv minus integral v du. You need to know that. uv minus integral v du. All right. Okay, you guys all did that. You paused it. You came back. Perfect. Perfect. Now let's look at some examples. Let's see how we use uv minus integral v du. Okay, number 1. Example 1. Let's say that we have x times e to the x dx. The first thing to do is to say, okay, can I do a u sub? That's the first thing you should always ask. Can you do a u sub? Because you don't want to go and use this if you can do a u sub. Not because it wouldn't work, just because it would be a lot longer process for you. Okay? So if you can use u sub, do u sub. Don't try to use by parts if you can just go do a u sub. If we were doing a u sub, the only thing I could do a u sub on would be my exponent here. So I would be saying u is equal to x. So du is dx. And I would have another x out here. So this would be the integral of u e to the u du. That was not a very helpful u sub, was it? All right. So this will be a good candidate for by parts then, because I see an algebraic function times an exponential function. So we're going to go off to the side. All right. I need to label one of these things u, and then everything else will be part of dv. Okay? I'm going to do a couple of examples with you, and you'll see what happens here. I'm going to start by labeling the xu. So u is equal to x. All right? U is equal to x, which means everything else is dv. So dv is everything else. Okay? So now this is the integral of u dv. Integral u dv. Well, this is now equal to uv minus the integral of v du. So I need to know what u is. Do I know what u is? Yes, I do. I need to know what v is. Do I know what v is? No, I do not. How can I find out? Well, I can just integrate both sides of this guy, and I can get what v is equal to, right? V, because the integral of dv is v, right? So the integral of e to the x dx is e to the x. Yes, there would be a plus c. I'm just going to put the plus c on my final answer, okay? So now I know what u is, I know what v is. Great! Minus the integral of v, which I know, du. Do I know what du is yet? Have I found du? No, I have not. So I need to find du. What is du? Well, du dx is just 1, and then we would multiply both sides by the dx. So that's just 1 dx, or dx, right? So now I can come back and write everything. This is equal to uv, so x e to the x, that's uv, minus the integral of v du, e to the x dx. So this is x e to the x minus the antiderivative of e to the x is e to the x, and here comes my plus c. Isn't that cool? I love by parts. I love by parts integration. It's so challenging sometimes. Here it was a little bit easier, not because it was just an x and just e to the x, but also we didn't have any coefficients or anything like that to deal with. But I love this. Love it. All right, let's see what we did there. This integral was, we got rid of the x, didn't we? We got rid of the x there, and that was helpful. Yeah? You always want to let u be something that's easy to take the derivative of, and if possible, that the derivative will be simpler than what u was. So we started off with x. When we take the derivative of an x term, it goes down in power, right? So u is nice to have an algebraic function for. Okay? dv, though, has to be something that you can take the integral of. So you would never let dv be something that you didn't know how to take the integral of. All right? Okay, let's do another example. Number 2. The antiderivative of 2x sine of 3x dx. Okay. So the first thing I would do is try to do a u sub. If we did a u sub, u would be 3x. du would just be a 3. Again, we have this extra x out here, and that's unhelpful for us. We cannot just do a plain u sub. We cannot do a plain u sub. Okay? Next thing I take a look at is, oh, it's an algebraic times a transcendental. So maybe I can use by parts. So that's what I would try. I would try by parts. I want to let u be something for which I can take the derivative of and get a simpler thing. So I'm going to let u be the 2x. If I let u be the 2x, then dv has to be everything else. So dv has to be sine of 3x dx. Okay? U was the 2x, dv is sine 3x dx. Okay? We always need to get du, and we always need to get v. So let's get du. Du will be 2 dx, right? Because du dx is 2. All right? For dv over here, we're taking the integral of both sides, right? So for dv, we have v is equal to, all right, what's the antiderivative of sine? Well, the antiderivative of sine is negative cosine, isn't it? Negative cosine. But we have that 3x. The derivative of 3x is 3. We need to undo that 3, so this will be a 1/3. You're going to get very good at doing quick antiderivatives with this section right here if you do your work. If you don't do your work, you still won't be very good at it, very quick at it. All right? So that's the antiderivative of sine of 3x. Now that we found that, we can come back over and write what what this antiderivative is. Okay? uv, so 2x times a negative 1/3 cosine of 3x, that's u times v, minus the integral of v du. Well, du is this 2 dx, so I'm going to multiply 2 times that negative 1/3, and I'm going to put that negative 2/3, I'm going to put that outside the integral. So that will make that a plus 2/3. And then I have the cosine of 3x here, and the dx from what part of du is. Okay? All right, so this is negative 2/3 x cosine 3x plus 2/3 times the antiderivative of cosine 3x. Well, the antiderivative of cosine is sine. And then we have to undo the derivative, so another 1/3 plus c. That would be a safe stop spot, but not a multiple choice stop. This will be 2/9 sine of 3x plus c. Okay? All right. Number 3. Let's say that we have the antiderivative of x squared e to the 3x dx. I put that really close to that previous problem. Okay, let's separate that. Okay. Well, first of all, I would go to the process. If I let u be this exponent, du is not going to have an x in it. I have 2 x's out here. So this is not a straightforward, plain old u sub. It's an algebraic times a transcendental, so I'm going to go off to the side and do u sub. I'm going to let u be the x squared, because the derivative will be simpler, right? And I'm going to let dv be everything else. We have to. We always have to do that. Everything else. Okay? So, du here will be 2x dx. V will be the integral of e to the 3x. Well, the integral of e to the 3x is 1/3 e to the 3x. Like I said, you're going to get really quick at doing these quick antiderivatives. It's e to the 3x. The derivative of the 3x is 3, so we have to undo that and make it a 1/3. Take the derivative of this, and you get right back to e to the 3x, right? Which is what an antiderivative should do. All right. So here we have uv, so x squared times 1/3 e to the 3x, or 1/3 x squared e to the 3x, minus the integral of v du. So I have that see the 2/3? That 2/3 I'm going to take outside of that integral. And then inside I have x e to the 3x dx. Okay? Which is equal to 1/3 x squared e to the 3x minus 2/3. What is the antiderivative of this? We have to do by parts again, don't we? I knew you would have to do by parts twice here because of this x squared. Okay? What if it was x cubed? X to the 4th. Right. we're going to go off to the side and do by parts again. We're going to let u be the x, and then dv will be everything else. So du is dx, and v is 1/3 e to the 3x. So this integral right here is going to be uv x times 1/3 e to the 3x minus the integral of v du. The 1/3 I'm bringing outside, and then I just have e to the 3x dx in there. Be careful with this because this 2/3 needs to be multiplied by everything in there, right? So be careful with that. I'm just going to keep my brackets. 1/3 x e to the 3x minus 1/3 times, what's the antiderivative of e to the 3x? 1/3 e to the 3x plus c. That would be a safe stop spot, but let's clean it up because for a multiple choice answer, they would definitely clean this up. Okay, this would be negative 2/9 x e to the 3x, and this would be, this is 1/9 here, so this would be negative 2/27 e to the 3x plus c. That would be the multiple choice answer. Let's take a little look at, see what kind of pattern we were dealing with here. We started with an x squared e to the 3x. Look at what was in our answer. X squared e to the 3x. X e to the 3x. E to the 3x. Do you see how the x's diminished each time? That's a nice pattern to see. Okay. Now, I would like to do the same problem with you. Let's see. Let's just go and do your next example that is listed in your sheet. Example 4. In example 4, we have the integral of 4x cubed sine of 2x dx. Well, when I see this x cubed, I know we're going to need to do integration by parts 3 times, right? Which you could. You could just go and do the same thing we just did and do it 3 times. But as we saw here, there is a bit of a pattern involved, isn't there? There's definitely a pattern involved. So what we can do on these is we can use that pattern, and it just makes things a little bit shorter, okay? This is called the tabular method for integration by parts. Okay, so here's how that works. We're still going to be doing the u and the dv, all right? We're just going to have a column for all of our u's. In this case, we'll have 3 of them. And we're going to have a column for all of our dv's. Okay, here's what we do. There's our 2 things. Write down what your first u would be and what your first dv would be. Our first u here would be 4x cubed, right? Our first dv then would be everything else. All right? Now, what do we do to the u's? We take derivatives, right? We take derivatives. So I'm going to take the derivative. I'm going to take the derivative of this. That's 12x squared Then I'm going to take the derivative of this, and that's 24x. I'm going to take the derivative again, and I'm going to take the derivative again. You take a derivative until you get down to 0. Okay? Now we're going to come to the dv's. What do we do to the dv's? Well, we integrate those, don't we? We integrate those. So the antiderivative of sine of 2x will be a negative 1/2 cosine of 2x. And now we need to take the antiderivative of this. Well, the antiderivative of cosine is positive sine, right? So this negative is going to have to stay. So it's going to be a negative 1/4 sine of 2x. And now we take the antiderivative. We're going to keep taking antiderivatives until we get even with this 0. All right? So we have 2 more to do. Antiderivative of a negative sine will be a positive cosine. So that's just going to be 1/8 cosine 2x. And then the antiderivative of cosine is positive sine. So this will be 1/16 sine of 2x. Okay? Just like in by parts, we never use our dv. The formula is uv minus v du. There's no dv in there, right? So this very first dv, you will end up not using. And this last derivative, the 0, you will not use. You're not going to use those. Okay? Here's what you do. We're going to multiply things together. We're going to start at the top. But before you start to multiply, there's something you need to remember to do. And what we're doing here is we're taking care of, this is going to account for this minus in the formula. This minus in the formula. This first term is going to start off positive because this is our u dv. So this first term is positive. Well, it's positive. It might end up negative, but we put a positive there. But the next one, we're going to make it a negative. And that accounts for that minus the integral of v du. And then positive, and then negative. So you're always going to start positive and then alternate the sign here. And now you're going to multiply diagonally because here's our uv, right? This would be the next uv, this would be the next uv, and this will be the very last integral. Okay? So our answer, we can go straight to our answer here. Our answer would be 4x cubed times negative 1/2 cosine of 2x. That would be a negative 2x cubed cosine of 2x. And then we have a negative 12x squared times a negative 1/4 sine of 2x. That's a positive 3x squared sine of 2x. And then we have 24x times 1/8 cosine of 3x. That is a positive 3x cosine of 2x. And then our last one will be negative 24 over 16, which would be 3 over 2 sine of 2x. And then we don't forget our plus c. And that's the tabular method for integration by parts. Real quickly, I want to go back to our previous problem, our example 3. Let's redo number 3 real quick. Number 3 was x squared e to the 3x dx. Okay, let's come and do that by using the tabular method real quick. U was x squared. dv will be e to the 3x dx. Derivative derivative, derivative, until you get to 0. Integral, 1/3 e to the 3x. Integral, 1/9 e to the 3x. Integral, 1/27 e to the 3x. Plus, minus, plus. Multiply, multiply, multiply. So this will equal 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x plus c. And that was quite a bit quicker than our process here. And we got a different answer. We got a different answer because I see here, I saw this positive here and we had a negative, but that was a mistake, right? Ooh, I'm so glad we caught that for the note's sake. Otherwise, I'd have to go back and redo these notes. I'm really glad we caught that. That would be, this is a case when in class somebody would say, oh, Miss Murray, that's a positive. And I'd say, oh yeah, you're absolutely right. Okay. But you can see this technique here kind of is helpful for that too, because you're not going to make those little mistakes as frequently. Okay, so I'm a big fan of the table method. I'm a big fan of the table method, and I will use the table method whenever I can. So when is it good to use the table method or the tabular method? When is it good to use the table method? I do it, you guys, when I have an algebraic, so x's times e to something, sine of something, or cosine of something. One of those. Okay? That's when I use the table method. Alright? Don't use the table method if you have a natural log. Okay? Not that you cannot, but it's not as straightforward. Okay? And you don't know what the integral of natural log is, so that's going to be an issue too. Okay? So don't use the table method. This is when the table method is really good, really quick. Alright? Don't use it when you have an inverse trig function. Okay? Just e to something, sine of something, cosine something. Use the table method. And we could have done it for every example that I've done with you so far. We could have done it for this one. We could have done it for this one. And clearly we could have done it for that one. And then definitely for this one. So I will even use the table method, even if it's just a plain old x, I'll still just use the table method. It's not quite as quick, it doesn't save you quite as much time, but that's okay. Alright, so table method is really friendly. Example 5. Antiderivative of x squared natural log x dx. Alright, I just said not a good one to use the table method on, and I'm going to say why. Definitely we need to use by parts here because we can't do a u-sub. U-sub won't work. So, by parts. So the question is what to let u equal? What to let dv equal? Alright, remember u has been something that's been friendly to find the derivative of. So it might be really tempting to let u be the x squared, but if you do that, then dv is going to be the natural log of x. And do we know what the integral of natural log x is? Do we know what that is? No, we do not. Not yet. Alright? So we cannot let dv be something that we don't know the antiderivative of or how to get it. So we have to let u be natural log x. okay? Which means dv is going to be x squared dx. All right? What's the derivative of natural log x? 1 over x. That was fine. Okay, over here, what's the antiderivative of x squared? 1/3 x cubed plus c, which we'll add at the end. All right? Okay, so this is going to equal uv minus the integral of v du. Do you see what happened there? We're going to have the 1/3. I'm going to pull the 1/3 out front. And then I have 1 over x times x cubed. Well, what's 1 over x times x squared? Didn't that work out nicely? Yes, it did. Because we know how to find the antiderivative of x squared. So this is 1/3 x cubed ln x minus 1/3 times 1/3 x cubed plus c. So the multiple choice answer would look like this. Okay? All right. So if there's a natural log, in here, that's your u. Let u be that. If there's any log in there, but it'll be a natural log in this course. All right. So that's what you should let u be first. Before you let u be the algebraic function, let u be that exponential function, or be that log function. Okay. Now that we know how to do that, we need to come and find the antiderivative of just natural log x dx. Okay? Let's do that. This is interesting. What function's derivative is natural log x? We have not done that yet. We've never had a function that when we took the derivative, we got natural log x. All right. This doesn't look like a by parts problem, but it is. Okay? This is by parts. You might be saying, wait, it's not even a product. But it is a product, isn't it? It's the product of two things right there. I'm going to let u be natural log x. I'm going to let dv be dx. So du is 1 over x dx. V is x when we take the antiderivatives. So over here we have uv x log x minus the integral of v du. Well, 1 over x times x is just 1 dx. So this is x log x minus x plus c. X log x minus x plus c. And now that we have found that, that would be a really nice one for you to know. This is the last thing on our formula sheet for the integrals. That's our last log. That's our last integral that you hadn't known yet. All right, x log x minus x plus c. X log x minus x plus c. In class, we would repeat that a couple of times too. All right, moving along. Number 7. Let's do the antiderivative of arc sine x dx. Okay. Again, this doesn't look like it would be a by parts problem, but it is. Okay, and also again, we've never had a function that when we take the derivative, we get arc sine. So this is how to do that. This is how to find that antiderivative. Okay. We're gonna do this kind of like we did the previous problem. We're gonna let u be arc sine of x because we know how to find the derivative of arc sine x. At least you did back in the previous unit. You may not remember now, but you used to know how to find the derivative of that. Hopefully you still do. We're going to let dv be the dx. All right, du, the derivative of arc sine, is 1 over square root 1 minus the argument squared. Okay? The integral over here is just v is equal to x. All right? So now we have uv, so x arc sine x minus the integral of v du. Do we know how to find that antiderivative? We do. By doing a plain u sub. The derivative of the inside is going to have an x in it, and there's my x. So this is plain u sub, not by parts, just plain u sub. U is what's inside that radical. Du is negative 2x dx, right? So negative 1/2 du is x dx, and I'm replacing x dx with negative 1/2 du. So this will be x arc sine x plus 1/2 integral or antiderivative of u to the negative 1/2 du, right? Pull that up, because now we're back to power rule. We have to use the power rule. So pull that up to the top to use the power rule on it. All right, so this is 1/2 times, so this will be u to the positive 1/2 times 2. And now it's time for your plus c. And now go back to x's. And there we go. You don't need to memorize that, but it's interesting. Okay, I've got one more example for you. Seeing how we do on time. Yeah, we're doing good on time. So number 8. What about this guy? So in this one, we have a product of two transcendental functions. So yeah, in this example, we have the product of two transcendental functions. So the question is, what do we let u equal? What do we let dv equal? It's always good to let u equal something that will kind of break down, right? Neither of these break down, do they? The derivative of e to the x is just e to the x. The derivative of cosine has a sine in it. So it's neither one of these break down. So I like, it really doesn't matter which you let u be, which you let dv be. I like to let u be the e to the x, but it really doesn't matter. Okay? If I let u be the e to the x, then dv will be cosine x dx, right? So du will be e to the x dx, and v will be the integral of cosine is sine. All right, so this becomes uv, so e to the x sine x, minus the integral of v du, so that's e to the x sine x dx. another by parts. Okay, now this is important. If you let the u be the e to the x up here, you need to let u be the e to the x down here as well, okay? If you had let u be the cosine x here, then let u be the sine x here, all right? Just make sure you stick with either both of them being the exponential or both being the trig, all right? In this case, dv will be sine x dx. So du is e to the x dx again. V is the antiderivative of sine, which is a negative cosine x. All right? So back to our expression here, we have e to the x sine x minus this whole thing, right? So put brackets. It's going to be a big one here. All right. uv, so negative e to the x cosine x minus the integral of v du. This minus I'm going to bring out and change this to a plus, and then I'll have e to the x cosine x dx. So this is e to the x sine x plus e to the x cosine x minus integral e to the x cosine x dx. At this point, do not do by parts again, because you'll see you would be in an infinite loop, right? Because this is the same thing we started with. So you need to recognize that. This is the same thing we started with, so stop by parts. The craziness would only get crazier. So stop by parts. And I want you to think about something. This is the same thing we started with. So this is equal to this entire expression, right? So I'm going to come down and I'm going to write that. I'm going to say, okay, what have I shown so far? I have shown that that integral is equal to this. That's what I've shown so far, right? Let's add this to both sides. It's an equation, so we can add it to both sides, right? What is this integral plus itself? Is that not two of those integrals? So two of those integrals is equal to this. Right? So what is one of the integrals equal to? Half of that, right? Plus c. Don't forget our plus c at the very end. As a multiple choice answer, I would probably factor out that e to the x. Is that not cool? Okay? That's a cool problem. Love it, love it. All right. Okay, time for you to go practice by parts integration. But before that, let's do one more time. So the integral of u dv is equal to uv minus the integral v du. Put that on a little sticky note and tape it onto your bathroom mirror so you see it every time you go in and wash your hands, okay? Also, we learned here what the integral of natural log x dx is. Do you remember what that is? X log x minus x plus c. X log x minus x plus c. That's another one that is nice to know. All right. Go practice.